contrast the results that we are obtaining in the paper with Elnaz Kanani and Elena Parilina. So the second part of the presentation will be very classical. I will start by telling you what we are after and develop the models and show some results, based essentially numerical results, and to conclude. Please interrupt me whenever you want if you have a question. Don't do it via the chat because I'm not able to handle it. So just interrupt me and ask your question. Okay, so first of all, let me give you a crash course on coordination in supply chain. So a supply chain is simply a set of companies that are involved in a vertical relationship. So one is selling to the other, and ultimately the last one in the chain is selling to consumers. We have different configurations that are of interest. One of them, which has been studied extensively in the literature, is the so-called bilateral monopoly, where you have one supplier or manufacturer and one retailer. Throughout the talk, I will be using indifferently supplier and manufacturer. Another case is when you have one retailer and several manufacturers are competing in the retail store. The mirror case is when you have one manufacturer and you have several retailers. One such example is a franchising system, and this is a dominant mode of organization in many sectors of the economy nowadays. And the most general case is, of course, when we look at a setup where we have several competing manufacturers and several competing retailers. Now, in terms of the lengths of the supply chain, you may have different various layers, and this will depend on the complexity of the product and the organization, the economy. And also, I would like to mention here that you have different layers in terms of physical intervention, meaning that the merchandise is changing hands, whereas you may have also some layers where the intervention is essentially financial. Now, let me focus from now on the most studied case, where we have one manufacturer and one retailer, and suppose that we are interested only in pricing decisions. We have here strategic interaction because the manufacturer is deciding on the wholesale price and the retailer is reacting by choosing the price to consumer. And this type of interaction is called vertical interaction. Now, we can operate this supply chain at least under two different modes. One of them is to have the chain vertically integrated, or to have the game played in a decentralized way. Obviously, if the chain is vertically integrated, the total profit will be higher than the profit under decentralization by definition. However, how much we are losing by implementing a decentralized system depends on the benchmark. Now, if in the decentralized system, the players are implementing a Nash equilibrium or a Stackelberg equilibrium with the leader being the manufacturer or the leader being the retailer, the outcome in the decentralized system will be different. And when we measure the difference between centralized system and decentralized system, this difference will depend, of course, on this. Now, what is interesting in the case of vertical integration is that consumer is happy. So this is a kind of collusion that consumers cherish, which is not the case when you have horizontal competition. Now, from where the inefficiencies are coming in the decentralized system, they are coming from the so-called double marginalization. Think about it in the following way. The manufacturer is deciding the wholesale price, and the margin is W minus C, where C is the unit cost. So it's selling to the retailer at W, and this is the margin. Now the retailer is putting a margin on this margin, and this is what is creating the inefficiency, and it's called the double marginalization. Now, of course, we know that vertical integration is good. However, it may not be desirable for some other reasons, or simply it may not be feasible. So the $2 question is that, can we mimic the result obtained in vertical integration by implementing some other contracts than really vertically integrated? And if the answer is yes, we will say that the supply chain is coordinated. Here are 3 examples of contracts that are successful in implementing the vertically integrated result without integrating. The first one is the 2-part tariff. It means that the manufacturer is selling to the retailer at a tariff that is made of 2 parts. One is constant and the other one depends on the quantity that is taken by the retailer. Revenue sharing, I will talk more extensively about it. And we have also so-called buyback contract. It means that in the contract, the manufacturer agrees to take back some of the quantities that are not sold by the retailer at a price that is lower than the wholesale price. So this is one way of incentivizing the retailer to order more. It has been shown that at least in simple setup, this approach can coordinate the supply chain. Now, talking more explicitly about revenue sharing, what is happening here is that the 2 parties agrees on sharing the total revenue. So think about it in the following way. The retailer is getting a share phi less than 1 and the supplier the rest. And here phi is exogenously given. It cannot be determined in an endogenous way. And suppose that the manufacturer is facing a unit cost CM and the retailer a unit cost CR. So the total supply chain unit cost is the sum of the 2. And the wholesale price, as I said, is W. So now we can express the retailer's revenue function in terms of Q, which is the ordered quantity. Now, once we have done this, we can write down the profit functions of the 2 players. So for the manufacturer is W minus CM multiplied by Q, and the retailer, the revenue function minus the unit cost, which consists in 2 parts, the wholesale price and the unit cost facing in the retail store, merchandising or something else. If the system were centralized, in this case, the 2 parties will maximize the joint sum of their payoff. And here, clearly, the optimality condition will give us what would be the optimal quantity to be ordered by the retailer. In a revenue sharing contract, the retailer payoff is written in this way. It's a share of the total revenue minus the cost. Now, if we optimize, we obtain also the condition for getting the optimal Q. And what we need to do here is to simply equate these 2 in order to get the optimal quantity. And from this, we can deduce what should be the wholesale price in order to implement a vertically integrated result without vertically integrating. So this result is general. It does not depend on the functional forms or whatever. For as long as the parties are interested only in pricing decisions, you can achieve this result. But I'm going to show later on that this result does not stand in our case, where we have a little bit more complicated system. Now, we have plenty of examples of revenue sharing. For those of us who are old enough, you still remember the heroic days where we went to Blockbuster store to rent a movie and bring it back 3 days later on. Probably younger participants do not know even what Blockbuster is. So during this period, Blockbuster had a revenue sharing contract with studios in Hollywood. Now, if you visit a fashion store and you see a particular brand, Hugo Boss or whatever, probably there is a contract based on revenue sharing between the brand and the department store. One industry that has used this type of contract for maybe 1 century is the oil industry. Here, it's an interesting case because revenue sharing helped in dealing with the asymmetry of information. You have a big oil company arriving in a developing country. They are looking for oil, and this company has probably much more information about the geology of the soil than the government. And one way of having a win-win situation is to say, I will give you the right to explore for oil and to produce oil, and after that, we share the production, which is similar to sharing revenues. Here are more contemporary examples. I will skip them for the sake of time, but I guess you know all these industries. Now, if we move to closed loop supply chain, it means that here we are looking at flows in both directions. The forward activities include what we usually consider when we have in mind a supply chain. Means someone is producing and selling to someone else. So you can include here new product development, design, procurement, marketing, sales, etc. And in a closed loop supply chain, we have some reverse activities, product acquisition, reverse logistics, etc. So here the idea is to collect back the used product for either recycling, remanufacturing, or simply for disposing of this product in a safe way. Now, it takes a condition to close the loop. One such necessary condition can be operations benefit. So in this case, the manufacturer would be producing with a cost that is with used components, that is lower than the cost of producing with new material. So there is an incentive to collect back used product. There might be also a marketing benefit when you bring back to the store your empty beer cans, you are buying others. So there is here also an issue of rebuying. Otherwise, the regulation may impose such reverse activities, collecting back used product. One topic that is hot nowadays is what we call extended producer responsibility. So the responsibility of the manufacturer does not stop by selling. They need to collect some used products. One question is who should collect this used product? Can be the manufacturer, the retailer, or giving it to another company, which we call third-party logistics. Another question that is interesting here is that can we do something in order to increase the rate of return? We want to incentivize consumer to bring back their used battery instead of throwing them in the garbage. So here some actions can be taken, either monetary actions to give some money back when you return the product, or also to provide information about the importance of recycling and so on and so forth. Okay. So what we should remember here is that if we want to deal with a closed loop supply chain topic, product returns are really important. Now, if we look at how this has been done in the literature, one part of the literature has assumed that the returns are simply given, either in a deterministic or a stochastic way, meaning that companies are not really investing in any effort to increase the rate of return. Otherwise, you can implement some controls in order to increase these returns. And in such case, the returns can be, for instance, a state variable, and you are investing in advertising in order to increase this return. Most of the literature has been static, meaning that we assume that we are already at a certain steady state, and the returns are coming back in a steady state flow. Few models have been really truly dynamic in the sense that the whole process has been modeled. If you are interested by this, we have a survey with Pietro that appeared in 2019. And for reasons I cannot understand, the Annals of Operations Research is republishing the paper in June 2022. They have an agreement with the other journals. So don't think that we are submitting our papers to two journals. It's their policy. So for the rest of the talk now, I'll be dealing with this paper with Elnaz Kanani and Elena Barilina. So in terms of setup and research questions, what we have here is the following. I have a supply chain made of one manufacturer or remanufacturer called M and one retailer called R. To incentivize the returns, the manufacturer is investing in so-called green activities. Think of these green activities as advertising or communication campaign, where the company is telling consumers about the importance of recycling and so on and so forth. Also, it may include some monetary incentives or not. It can be symbolic. So all these activities, we are summarizing them under the title of green activities. We are going to determine the result in 3 scenarios and to contrast them. One is, which is the main part, reverse revenue sharing contract. Here, the retailer is sharing the cost of the green activities with the manufacturer, and in return, the retailer is receiving a discount on the wholesale price. Okay. Here, because the manufacturer will be producing with used components, it gains something, and this something is shared with the retailer. The other 2 models are standard one. One is the wholesale pricing business model. It means that the manufacturer set the wholesale price and the retailer the retail price. However, the story I will be telling here is a little bit different. And we have the case of vertical integration simply as a benchmark to compare how good are we doing with this RRSC contract. In the 2 first models, I will be assuming that we will be considering a Stackelberg equilibrium where the retailer is the leader. So we have here 3 important ingredients, and we do not want to miss any one of them. One is that there is a strategic interaction between the 2 agents. When you see this, it means that you need a game model. Second one is that the product returns depend on how much sales have been in the past. So there is here a history-dependent nature of product returns. So it means that you need really a dynamic model to be serious. And third one is that if you are dealing with long-term, the demand should be considered as uncertain, and we need a game that accounts for this. So when we have these 3 ingredients, we can adopt the so-called dynamic game played over event tree framework. In this case, we have a stochastic game. However, the stochasticity is not driven by the player's actions. This is the main difference between a DG PET and a truly stochastic game as is understood by game theorists. Now, we know that in a dynamic game, the result depends heavily on the class of strategies we consider. Typically, we have considered in the literature open loop strategies, feedback strategies, or Markovian strategies, and history-dependent strategies, namely that we have non-Markovian strategies. In a DG PET, we are going to use so-called S-adapted strategies, where S stands for sample of the stochastic process. In this case, the strategies are adapting to the stochastic process, but not to the whole state. So the stochasticity can be part of the state of the system, but we are not fully feedback as in a feedback, truly feedback equilibrium. So essentially here, the decisions depend on the history of the stochastic process, and I will show you later on what does it mean. So the questions that we are after, one is to characterize the equilibrium strategies. Second, we are intrigued to see if a revenue sharing contract will be Pareto improving with respect to a no sharing equilibrium. As I have showed in the cartoon example before, it's always the case. Here we would like to see if this result stands also. And as typically in this kind of situation, we want to look at some sensitivity analysis. So the first ingredient that I need to introduce is the tree. So suppose that we have capital T periods, and we have random demand. This random demand is defined by a stochastic process over an event tree. We need a root node, and at each period, we have a set of nodes, calling it NT. Any node at period T has a predecessor or antecedent, and this will be denoted A and T. The set of successor is denoted S of NT. Pi superscript NTL is the probability of passing through this node. The probability of passing through the root node is 1. And we have probability of the single scenario terminating at leaf or node at a terminal node. And of course, this sum should be equal to 1. So here what we have in mind, we have a tree. We have here 6 periods running from 0 to 5. So the stochastic process is given, meaning that the tree is defined by someone else, by a consultant, and the probabilities of going from one node to another is also given. Now, of course, we can do a lot of sensitivity analysis after that to check what would be the impact of varying these probabilities. Now, coming back to the information structure that we have here, the S-adapted information structure, if the game were played in open loop strategies and I am at T equal 2, in all these nodes, the decision would be the same, okay? However, in our setup, the decisions at this particular period will be adapted to the nodes, meaning that here I may produce something very different from here and from here and from here. And this is what we meant by saying that decisions are adapted to the stochastic process. Okay. Now, when we have a pass running from the initial node to the terminal node, is called a pass without any surprise. So here we are using the terminology essentially of stochastic programming. What is really nice with such structure that if you are here, it means that all other nodes are now irrelevant. Okay, so it's, as time is passing, part of the tree is becoming irrelevant. Okay, so the price at each node is chosen by the retailer, and I'm having here a demand that is linear in the parameters. So from now on, when I have a variable, as variable depends, the value depends on the node will appear as an argument, whereas when it is a parameter, it will be a superscript. Okay, so suppose that we have a demand like this one, and these alpha and beta parameters are varying across the tree. Denote by Rn the T, the returns at that particular node at any one of these periods. We can think here of the meaning of a period as a consumption cycle. It can be short if we are dealing with soft drinks, medium if we are dealing with water filters, or long if we have smartphones or laptops. The main point here I'm making is that the length of the period or the duration of the period depends on the type of product that we are considering. Here is our main assumption that the returns at any node depend on the investment in so-called green activity program at the previous node and on the quantities sold at all preceding nodes along the whole path. Okay, so what is a path of this particular node is simply a succession of nodes going from N0 to this node I'm considering. So I can write now the vector of quantities along this path as the quantity sold at N0, the quantity sold at this particular node, and so on and so forth. So I can track all quantities that were sold along this path. So the returns at any node are given by the following nice formula. What do we have here? I am at this particular node at period t, call it L. So at the preceding node, this was the quantity that has been sold. I'm assuming that part of this quantity will come back to the manufacturer, and this part depends on the investment during the same period, same node in green activities, multiplied by a scaling parameter θ1. And since consumers are not obliged to bring back the product immediately after consumption, maybe some quantities sold 2 periods before will come back during this period, etc., till I reach the original node. The zetas are simply scaling parameters, and the assumption here is that they are decreasing over time, in the sense that recent past has more importance as remote history or past, simply because of forgetting. Consumers forget about bringing something, and this product ends up in the garbage at a certain moment. Now, we would like to model this efficiency function of green activities. We want to have the following properties. It has to be between 0 and 1, because I want to avoid having more returns than what I sold in the previous period. And also, it makes sense to assume that this function needs to be concave increasing in order to account for marginal decreasing returns. Okay. So one candidate for such function is the following one. So I have mu1 minus mu1 minus mu2 e to the capital kappa g. Kappa is positive, and the other parameters mu1 and mu2 are between 0 and 1, with mu1 larger than mu2. So if the manufacturer is not investing at all in G, meaning setting G equals 0, F0 will be equal to mu2. And this is what we call in the literature passive returns. Okay, so without investing green activities, some good consumers will be bringing back the used product without any incentive. On the other hand, if I let G goes to infinity, this Fg will be equal to mu1. So this is the maximum efficiency that I can achieve, and this is less or equal to 1. So note here that I have something which is not linear, meaning that I will end up with dynamics that are not linear, as we often see. So clearly here, the returns at this particular node depends on the entire sale histories, and this is, from an econometric perspective, is very costly. It means that you need to estimate T parameters in order to get an estimation of all this. In our framework, we can do it because everything is done numerically, and we don't care. Just give us the values of zetas, and we can run the algorithm. However, often in the literature on time series, we make an assumption of geometric decline concerning these scaling parameters, namely that the ratio of two successive parameters is constant and equal to, say, eta, and this eta is between 0 and 1. Now, under this assumption, the return dynamics now are much simpler. Simply, we have the returns at this particular node. It's a fraction of the returns at the antecedent node plus what we have sold at the antecedent node multiplied by this efficiency function and multiplied by this θ1. So we have here the dynamical system that is much more sympathetic than this one. However, it comes at the cost of making this assumption of geometric decline. If θ1 is less or equal to this ratio, we can guarantee that the returns are always less than or equal to past sales. because we don't want to have more return than the number of units that we sold in the past. Note that this is a sufficient condition. It means here we are assuming that the manufacturer is investing in GA at its upper limit, at infinite value. So the bound here is very, very far from being tight. What do we have else? We have the cost of investing in green activities. We are taking here a linear one, but we can have a quadratic or any convex cost. It does not matter. Again, we are solving numerically. Now, what are the benefits of the returns? These benefits are materialized in the decreasing unit production cost. So the cost with these returns is given by this function, which is convex decreasing in R. So C0 is the unit production cost if you use only new material, and CR is the reduction in cost that is due to the returns. So what are the benefits of the returns? We can think of the returns themselves as the environmental performance. Instead of having batteries ending in the landfill, they are ending at the right place. So this is the environmental performance. Now, in terms of economic benefit, is given by this. So instead of producing with C0, we are producing with C0 multiplied by this difference. Okay. Now, I note that the wholesale price we are considering is exogenously given, and it's bounded like this, meaning that we want to have a positive demand at if we sell at the lowest possible price. So here are the different models. In the no sharing scenario, what do we have? We have the manufacturer maximizing with respect to the green activities. Pi is the probability of passing through this node. Delta is the discount factor. W minus C of Rn is the margin multiplied by the quantity minus the cost of green activities. And you take the sum over time and over all nodes. For the retailer, the maximization is with respect to the retail price. Again, we have here the probability of passing through this node multiplied by the discount factor. This is the margin, the price minus the wholesale price, multiplied by the quantity, subject to the dynamics that you have seen before. So this is the case of no sharing scenario. In the case where we have reverse revenue sharing, let me denote by B at node NT the share of the cost that is paid for by the retailer of the GA green activities cost, and B is between 0 and 1. Now, as the retailer is participating in the green activity cost as a good gesture, the manufacturer is reducing the wholesale price, and the reduction is given by this. It's W minus this incentive function that depends on the return. Now, one common incentive function in the literature is the following one. So this is phi. It's a number between 0 and 1, where we have W minus the cost of producing with returns, and this is giving us the reduction in the wholesale price that is offered by the manufacturer to the literature to the retailer in order to implement this revenue sharing contract. Now note that this I is increasing in returns, so it's playing really its role of incentive. Phi is the percentage of M's profit margin that is transferred to the retailer, as I said. Now, what are the reasons for having a wholesale price that is exogenous? If it were not exogenous, now in this case, what the manufacturer can do is to play out to the retailer by saying that I'm giving you an incentive to help me in the GA cost, but at the same time, the manufacturer may be raising the wholesale price. So at the end, we lose this idea of incentive. So this is the reason why we don't have these 2 degrees of freedom by setting the incentive and setting the W. It makes sense from an optimization and incentive points of view. So the optimization problems in this case, for the manufacturer, again, you see here probabilities, discount. What has changed here is that the margin is now reduced by the incentive that is given to the retailer, and also there is this part of the cost in the green activities. Whereas for the retailer is getting additionally to the benchmark case this amount, incentive, which is a reduction in the wholesale price, but it is contributing into the green activity programs, and the dynamics are given by this equation. In the case of vertical integration, this is no more an equilibrium problem, it is simply an optimization problem. And the assumption here that the two parties agree to maximize the sum of their profits. And this is a problem that is much easier to solve. It's an optimization problem rather than an equilibrium problem. Okay. So first proposition, this is what we have under the no sharing scenario. So what can we exhibit here? We can show what is the green activity equilibrium level at any node. And this equilibrium level is depending on all parameters. And more importantly, it's depending on this phi functions. And what is this phi? This phi is accounting for the marginal value along the successors. I will give a more interesting interpretation in a second. What I would like you here to realize is that the solution is not fully explicit in the sense that the adjoint variables here are given in a recursive, as a recursive system. So when you want to solve it, you start by solving at the end node and you go up in the tree in order to get this marginal value of the returns at this particular node. So this is the co-state variable. You see here that the equilibrium is not that nice to show, but still we can get a few insights. The first one here is that Nash and Stackelberg equilibria coincide. So it does not matter if the game is played with leadership or simultaneously, the result would be the same. The reason is that the problems are in fact largely decoupled. So it does not matter. In the literature, we always discuss how the price varies with the wholesale price. And we say that there is strategic complementarity when the retail price is increasing in the wholesale price. So you can see it from here that this P is increasing in W. However, here I'm using strategic complementarity in a metaphor sense because W is a constant. Now what we have is a condition under which we have an interior equilibrium for the green activities. And if this condition is not satisfied, it means that these green activities are set equal to 0. Now, in terms of how the level is determined, it's given by this formula. It may appear complicated, but it's not. So this is how the returns are varying with respect to G. And this is the marginal benefit given by the adjoint variable. So what we have here is on the left-hand side is the marginal cost, and on the right-hand side, we have the average future marginal benefit at node and LT. And this marginal benefit is propagating through all successors, and everything is scaled by the discount factor. So although proposition is not nice to write, and we cannot solve completely. I mean, it's explicitly stated, but in order to have everything explicit, you need to solve back this system. Now for the other two cases, I wanted to show you the results in the reverse revenue sharing contract, but I tried really different ways of showing the result, and I could not do better than in 5 slides. So I said in this case, it's useless to show the results. So I'm not showing the proposition, but it looks something like this, but multiplied by five slides. And why it is the case? Because everything is really coupled. And it's much harder to get qualitative insights, although we can always say a few things regarding the relationship between marginal cost and marginal benefits. So what we are providing also in this proposition are the conditions to have an interior Stackelberg equilibrium. And this is important. You will see why in a few minutes. As we expect here, the investment by the manufacturer in the green activities is going to depend on the participation rate and the cost by the retailer. So the higher the participation rate, the higher the level of investment in green activities. And this participation rate is simply playing its usual role of being an incentive. In the case of vertical integration, as one can expect, it's much simpler because we are dealing here with a dynamic optimization problem and not an equilibrium problem. As it is typically the case, the result will be independent of the wholesale price, because when we sum the two objectives, the wholesale price vanishes. And by virtue of vertically integrating the supply chain, we are eliminating also the double marginalization. Okay. So what we can get from here, essentially numerical results. And now we need to organize a little bit the numerical simulations. Let me recall here that we have 13 parameters, 2 parameters related to the demand function. We have 3 cost parameters, the initial cost and the reduction due to the return and the marginal cost of green activities. In the dynamics of the returns, we have a number of parameters that I have shown previously. We have the wholesale price. And as I said, in this sharing revenue setup, the revenue is given exogenously. I have been thinking for really a long time about finding a way of endogenizing it in a game, and it's not easy. And delta is a stochastic, the discount rate. Now, if we have a binary tree and 6 periods, because of the stochastic demand parameters, we end up here with 137 parameter values. And of course, we have to do something about them to run some comprehensive simulations. So here what we are assuming that simply that the parameters, the stochastic demand parameters are evolving over time in the following way. So at each node, you can go either up or down by a certain factor. And similarly with beta, so when alpha is increased, beta is decreased, and this is the reason why it's minus plus and not plus minus here. So in this case, you save a lot on the number of parameter values. And as I said, once the program is installed, you can run simulations at will. And of course, some of the parameter values are normalized. Think about some parameters that are not so crucial for our understanding of what is going on. So what are the results? First of all, one difficulty that you have to realize when we are dealing with a setup like this one is talking about results. It means that implicitly we have to choose along which path we are going to show the results. the results along this path may be very different than the results along that one. So when we show the results, we have to choose some of the paths that we think are more interesting or help in contrasting what we are after. Anyway, so suppose that we have these parameter values. They are of no particular interest to you for the moment. What do we get? We get here the profits under the no sharing and the revenue sharing contract and vertical integration. So without any surprise, the vertical integration is giving the highest total profit. Of course, in the case of vertical integration, how we share this total depends on some other agreements, because what you obtain is the total profit, and after that, splitting between the two is a negotiation issue. So this result is fully expected, and the other result is expected that the revenue sharing would do better than the no sharing. And this is what we are getting. Is it always the case? We will see. Roughly speaking, what we are getting here as total profit for the whole supply chain is somehow in the middle between the two benchmark cases, the no sharing and the vertically integrated case. This slide is the one I like best. We are showing here result for some positive realization of the stochastic demand. It means that the demand is going up through different nodes. And what do we have? We have here what is happening at different nodes in the no sharing case, the RRSC scenario and the vertical integrated scenario. Now, if you look at the investment in green activities at any node, the green activities are going up when we move from no sharing to vertical integration. This is expected. So this holds true for all nodes. Under vertical integration, we invest more in NG. The price, on the other hand, goes in the reverse direction, meaning that consumers should be happy if the supply chain is implementing a revenue sharing contract. The price is going down, and it would be much better, of course, if they integrate completely. Okay. Now, in terms of return, think of the returns again here as the environmental performance. The environmental performance is going up when we move from no sharing to revenue sharing to vertical integration. Now, why I like very much this slide is that because here we look at the investment in green activities and what is the share that is taken by the retailer. So here you see that this share is 0. Now, for those of you who are familiar with cooperative advertising, and I have in my career committed a series of papers in this area, we always found this rate to be positive. And suddenly here we are obtaining a 0 rate. Why? The results can be due to only two things. One is that in the literature, we are disregarding corner solutions systematically and looking only at interior solution. The other way here is that it's coming from the stochasticity. It depends if you are going up or down. If you are going up and demand is increasing by itself, maybe there is no need to incentivize in this case. Everything will be working quite nicely. So what I want to highlight here is that really what this exercise allowed us to see clearly, something that I didn't see before in the literature, is that here the incentive can be set equal to 0 in under certain conditions, and it shows clearly that it's important to consider a stochastic demand. Now, when we look at revenue sharing contract and we want to check if this revenue sharing contract is Pareto improving with respect to no sharing, so here we are running a simulation taking different phi values. Remember that phi is the share of the manufacturer or the retailer, I don't remember. Anyway, the share of one of them. And what we see here is that if you exceed a certain threshold, now it is not anymore Pareto improving. So for instance, if phi is equal to 0.5, of course, the retailer is immensely happy. However, the manufacturer is not happy. So what is the main takeaway here is that depending on the revenue sharing parameter, you may not have the standard result that a revenue sharing contract is Pareto improving with respect to no sharing. Of course, this result is obtained for this parameter constellation. For others, it will be different. Either it will be always Pareto improving, or the level or the threshold where it starts or stops to be Pareto improving may be lower. But what I wanted to highlight here that we have indeed showed the existence of cases where we don't have Pareto improving. Now, in terms of the impact of the wholesale price, as it is exogenous, we can run a simulation with different values. And what we see here is that, again, for some values, revenue sharing contract is not Pareto improving for the manufacturer. For instance, if the wholesale price is at this value or that value, the manufacturer would be losing accepting a revenue sharing contract. So again, this is a nice result in the sense that it shows that this revenue sharing contract can do a lot of miracle, but not always. Let me skip this for simply showing different values here for the different variables and payoff. So what are the main conclusions here? Let me wrap up what we have. I sincerely believe that having a stochastic demand, if you have something long-term, is a natural assumption. What we have discovered here, contrary to the tens, if not a couple of hundreds of papers dealing with cooperative advertising, is that the support rate may be zero. It's not always positive. There are bounds on the sharing parameter in order to have Pareto optimality of the revenue sharing contract with respect to the wholesale business model. And this gives somehow an idea about the negotiation to take place between the parties when they are implementing a revenue sharing contract. This slide was meant to show that the reduction in production cost may not have a big impact on profit. In fact, here, for instance, if I take CR and I multiply it from 0.3 to 0.6, and you see the difference here in terms of payoff, it's surely not 100%. So it may be much smaller. Now, the inefficiencies that I talked about in the beginning, namely the inefficiency between vertically integrated scenario and other scenarios, here is going to depend on the path we are considering. If it is a very good one in terms of demand increasing, the result may be very, very different from having a path where demand is going down. Some extensions, empirical calibration, there is a literature dealing with evaluating the returns using some econometrics. So maybe for calibrating the model here, the famous CITAs I was talking about, they can be obtained empirically. We are assuming here that the returns are for operations reason, reduction of the cost, but they can be also demand enhancing. Used part can be used only a few times. Here implicitly I'm assuming that there is no bound on this. Also, remanufactured products are sold as new, but it may not be always the case. We can think about having monetary incentives to consumers to return the product, and also, of course, consider competition. Nowadays, you have remanufacturers who are eager to get returns even from other brands in order to reduce their production costs. So there is competition in the returns market. I haven't seen many game work in this area, and it may be interesting to look at this. Thank you for listening. I'll stop here and be more than happy to answer questions if you have.
Thank you, George, for a wonderful presentation. I think we have a few minutes for questions. So please go ahead, unmute yourself if you had any.